everyone, and welcome back to Causality with Boris, all broadcasts from Sobolev Spaces. In this video, I talk about outcome models, our first approach to replacing direct stratification with regression modeling. You will learn how to estimate treatment effects using outcome models. Here's the three main topics in this video: probability outcome models, mean outcome models, and covariate selection. Make sure you watch till the end to review the takeaways and compare them with your notes. As always, there is an extra material for this video. Click the link in the description and the PDF will be sent to your inbox. Stratification has a major drawback. It requires a lot of observations, especially if there are many strata. And within each stratum, we need enough data to split between treatment groups. In our running examples on the time and mortality association, there were 64 strata and 4 treatment groups within each stratum. Our database counted 140,000 observations, which is around 500 observations for each group, for each strata, on average. That's a lot. What do we do if there is not enough data? We model. That's right. This is the least discussed aspect of the modeling industry. And yet we do resort to regression modeling to compensate for the paucity of data. If expected outcome doesn't come directly from data, then we model the link between the outcome and some variables and estimate parameters of the model. You may heard modelers say things like, we adjust the association between treatment and outcome for covariates, or we control for covariates. Make no mistake, it's all done to figure the outcome probability in treatment groups for combinations of conditioning variables, the same variables that could define strata if they had enough data. Here is the rationale. A treatment effect is a change in an outcome. It's caused by receiving one treatment instead of another. Adjustment formulas estimate the average treatment effect. How is it done? Using means of expected outcomes for each treatment level. If there is enough data to estimate the expected value of the outcome as a sample mean, then it's the data we use. If not, we fit the regression model, then compute the mean outcome for each combination of treatments and covariates. Then we average the modeled outcomes over all combination of the covariates in the study population. This type of regressions is called outcome models in the causality literature. And there are two distinct approaches to modeling outcomes. One for binary outcomes and another for continuous outcomes. In one approach, we model the outcome probability, in the other, it's the mean value of the outcome. Let's take a closer look. Regression modeling. It extends the idea of using sample means. Instead, it exploits a fit regression model to figure out expected outcomes. Regression models link the outcome probability with treatment choice and other covariates. It all sounds reasonable, yet modeling comes with a lot of assumptions. For starters, the functional form that links the outcome probability to variables. It could take a form of logistic regression. It could be probit models or splines. Then there are assumptions about regression coefficients. Take, for example, a very popular logistic regression model. What's the assumptions there? A uniform increase in the log odds of outcome for every 1 unit increase in the regression variable. It's called a linearity assumption. But it can be totally unrealistic. Let's consider age as an example. In advanced ages, 1 year increase could add more to the outcome probability compared to early ages. Now let's consider the binary treatment case. There are 2 potential outcomes for each individual U. Y0 of U, it's the outcome if unit U doesn't get the treatment, and Y1 of U, the outcome if it's treated. Each unit U comes with the set of covariates ZU. To get expected outcome probabilities for each treatment, we use a previously fit logistic regression model, and then enter the values 0 and 1 for treatment variable. First, we compute the probability that y0 of u is equal to 1, that's expected value of the outcome for being untreated, given the values of the covariates zu. Then, we compute probability that y1 of u is equal to 1. We use the same model with the same values of covariates zu. We just switch treatment variable from 0 to 1. Then we average the expected probabilities over all patterns of z in the study population. What does this average define? It's the marginal risk of the outcome as if everyone was treated, and then separately as if no one was treated. What's the treatment effect then? The difference between marginal probabilities, capital P1 and capital P0. Causal reasoning involves comparing expected outcomes between all treated and all untreated populations. If the outcome variable is continuous, then we compare marginal means. Again, the binary treatment case for simplicity, control treatment and treatment of interest. There are two potential outcomes for each individual unit u. Y0 of u is the outcome if unit u doesn't get the treatment, and y1 of u is the outcome after undergoing treatment. Same as with the binary outcome, each unit u comes with the set of covariates zu. Here is the difference with the binary outcome modeling. To get expected outcome, we fit two outcome models, one for the treatment group and a separate regression for the control group, one for each values of the treatment variable. Then we compute the expected outcome for untreated. This is the mean of y0 of u given the values of covariates zu. To get the mean of y1 of u, we use a separate model, but the same values of covariates zu. This is the expected outcome for treated. We use two different regression coefficients for covariates z, for treatment and for control groups. Then we average the expected outcomes over all patterns of covariates z in a study population. Averaging gives us marginal mean of the outcome as if everyone was treated, and then separately as if no one was treated. Treatment effect is the difference between marginal means, capital E1 and capital E0, and it's dependent on the average of the covariate z now. What's the role of the backdoor criterion in all of this? It provides a guidance for selecting condition covariates, and it doesn't change whether we use stratification or regression outcome models. That's not a surprise. Modeling addresses a technical issue of data availability. How do we estimate conditional means and risk from data is a technical question, not a conceptual one. It doesn't change the fundamentals of the backdoor criterion. Consider treatment X and outcome Y. We select a set of variables Z that satisfies the backdoor criterion. They're supposed to block the influence of all other factors on X and Y. Post-regression analysis computes the expected means for X set to 1 and then X set to 0, but in both cases holding condition covariates Z constant. So stratification and regression adjustment, or regression modeling should I say, are the same methodology conceptually. There is just more and restrictive assumptions for regression analysis. There are several reasonable strategies for covariate selection. For example, all immediate causes of treatment in DAG. Markov assumption provides a guarantee that holding the patterns of treatment constant will block all other influences on treatment and outcome. In practice, this approach may produce too many variables, and there are some restrictions on the number of observations per regression variable, which will bring us back to the same data availability issue, the same issue that we were trying to solve by transitioning from stratification to modeling. We are really interested in minimally necessary set, and that comes from the backdoor criterion. It would be ideal if the adjustment set is a subset of immediate causes of treatment. We would say Regression modeling addresses the treatment selection bias explicitly, on top of everything else. But examine the criterion carefully. It doesn't say that the conditioning variables are good predictors of treatment choice. We just need conditional means for each treatment given conditioning variables. Recall the role of conditioning variables. They are here to block non-causal paths between treatment and outcome. Paths that can transmit the influence of all other factors and produce non-causal covariation between treatment and outcome. The main message of this video: we resort to regression modeling to compensate for the paucity of data. You learned that we use fit regression models to find the expected outcomes for each combination of treatments and covariates. Then we estimate the average treatment effect by averaging the expected outcomes over all patterns of covariates in the study population. You learn to use a two-model approach when the outcome is continuous. This is a very important idea, so please don't miss it. We fit two outcome models, one for the treatment group and a separate regression for the control group. And there are two different sets of regression coefficients, one for treatment and one for control group. If you're interested in learning more about the two-model approach, then check out my extra material for this video. Follow the link in the description, register your email, and the PDF will be sent to your inbox. Keep on watching.